Hello, everybody, and welcome to a brand new series. This series is a continuation of sorts of a series that we already have on this channel, which covers JavaScript from basic level to intermediate level. This series is intended to build upon that, so it is highly recommended that you have some sort of foundational JavaScript knowledge before continuing on with these concepts. So this series is divided into 4 main modules. In the first module, we'll be talking about object-oriented programming. Then we'll be understanding how JavaScript executes code. We'll be looking at modern and clean architecture. And finally, in the final module, we'll be looking at how senior developers actually build applications in JavaScript. For the first module, we have 4 episodes. And in the first episode, which is this one, we'll be talking about the 4 pillars of object-oriented programming. So that brings us to procedural versus object-oriented programming. Before OOP or object-oriented programming, we had procedural programming. This style divides a program into a set of functions. You have data stored in a bunch of variables and then functions that operate on that data. This is simple for small scripts, but as your program grows, you end up with functions all over the place. You copy paste lines, you change one functions, and 3 others break. This is what we call spaghetti code. There is too much interdependence. Next, we have object-oriented programming, which is much cleaner, where the structure is divided into objects so that every object and its properties and methods are independent of other objects, so they can run with much less interdependence. Open up your editor and let's create a new file, script.js. Alright, inside your file, let's say we're building a payroll app. In procedural style, we store our data in independent variables. So we have our base salary. So base salary variable, let's say 10,000. Then we could have an overtime. Let overtime equals to 10 hours. And we have the hourly rate, so 20. Now we need a function to calculate the wage. Because the data is separate, we have to pass everything in as an argument. So to create a function, function keyword, followed by the function name, followed by the parameters. So base salary would be required, overtime would be required, and rate would be required. Inside the function, we simply return a calculation, which could look something like base salary plus overtime times rate. And to use it, we have to pass every single value manually. So if I'm storing the wage inside a variable and calling the function, I'd call the function and pass in every value manually. Base salary, overtime, and rate. Now simply if I console.log our wage, I have an extension installed on my VS Code called Code Runner, which allows me to run my VS Code scripts in my terminal itself. So I get 10,200. So this works. But look at this. The function depends on 3 different variables. If I change one, it might break the function. This is highly coupled. Now let's look at the object-oriented way. Instead of having all of our methods and our values laying around in the open, we create an object. So to create an object, simply use the let keyword and start typing your object name. We're going to create an employee object. Inside our employee object, make sure you're using curly braces to denote that it's an object. Let's move in all our values inside our employee. You might get a bunch of errors because this is not standard procedure for storing values inside objects. Inside objects, we have key and value. So remove the let keyword, remove this semicolons, and remove all the other let keywords. And instead of an equals to, we have a colon. So this is our key and this is its respective value. There's still an error because you actually need commas. Now let's move our function inside our object as well. And instead of defining function here, we use the key for the function name, and in the value, we simply type function. It actually does not need any parameters. Why? Because it has direct access to the properties inside an object by using the this keyword. So instead of having a bunch of parameters, simply remove them. And instead of simply typing base salary, give this dot base salary, this dot overtime, and this dot rate. We will be looking at this keyword in great detail throughout the series in future episodes, but to simply put it, this keyword basically references the object that called the function. Let me remove all of this, and now to calculate wage, we ask the employee object to do it. So simply just wage would be inside employee dot get wage. So in this case, the getWage function is being called by the employee object. So the this represents the employee. So this dot base salary simply represents employee dot base salary. This keyword simply just references the object that is calling the function. This was an example of encapsulation.
Alright, the next pillar that we're going to be looking at is called abstraction. Think of a DVD player. It has a complex logic board on the inside, but all you see on the outside is a simple play button. We can do this similarly in code. Let's create an employee constructor. It takes our salary data. So create a function, employee. You can have your base salary, and you have your overtime, and you have your rate. Inside this dot base salary equals to base salary. This dot overtime equals to overtime, and this dot rate equals to rate. Now imagine calculating a complex tax or bonus. We don't want the outside world to be able to call this or mess with it. So instead of attaching to this, we declare it as a simple local variable. So let calculate bonus be a function that simply just returns our base salary times 0.1. Then we expose only the essential method to the outside world. So this dot get wage equals to function, and then this is our get wage function. If we create a new employee, so const my employee equals to new employee with a 30,000 salary, overtime 10, and a rate of 20, I can access this get wage function, but I cannot access this calculate bonus. It is completely hidden. This is called abstraction. It prevents other developers from breaking the internal logic of your objects by restricting access. So I can access the base salary, overtime, rate, and the get wage function. So I can simply just call my employee dot get wage, and this would return the wage as it did in previous examples. Our third pillar is inheritance. Let's say we're building user interface element. We have a text box and a select dropdown. Instead of defining the same properties over and over, we define them once in a generic parent class called HTML element. So let's create a class called HTML element. And inside the class, we want a few things. So we want our constructor. It should be not hidden by default, and its inner HTML by default should be empty. We have a method inside it called click, and once clicked upon, we're simply just console logging element was clicked. Now, when we create our specific elements, we just tell them to inherit from the parent using extend keyword. So when we create a class, we can simply extend, and inside our constructor, we can call super, and we can have additional properties as you want inside your text box. And obviously, you can have multiple classes that inherit the properties. So class select, create a constructor, call super, and options. So options is just a property that's exclusive to the select class. So what's happening here? We've learned about classes before. So what happens is instantly when you declare the text box class and select class, it gains the hidden property, the inner HTML element, and the click method. We eliminated redundant code. So every single class that you create that extends the HTML element class, so this is your parent class, all of the properties inside your parent class, so hidden, inner HTML, the click function, everything is already inherited by these classes. So if you simply just create an object using this class and try to access the .click method, it would simply work. Inside our constructor, we're calling super. So what does super actually do? Super simply calls the constructor of the parent class. So this is what's being called when you type in super. If you don't type in this, this will simply not be called. And of course, you can have additional values to your liking that's specific to the class that you're creating. If all of this is a bit confusing, please make sure that you go back and learn what classes and objects are in JavaScript and come back to this video. Finally, let's talk about polymorphism. Poly means many, morph means form. Let's say we want to render these elements. In a procedural world, we have to write an ugly switch statement to check the type. Let's start by showing you how you would render all of these elements using a switch statement. So you'd create a function that's named render elements, and you pass in your element, so likely a list. And for let element of elements, you simply run a loop, and inside the loop you run a switch case. So switch element dot type. If it's a text, then render text box and break. If it's a select element, then render select and then break. If it's a checkbox, you render the checkbox and then break. So on and so forth. So what we're basically doing is when you want to render elements that you've created using JavaScript on the screen, then we call a function called render element. In it, we pass different elements in the form of a list, likely. The for loop simply loops through every single item of that list, with every single item being stored in the element variable one by one. We're switching, so switch case simply just checks something. So what are we checking? We're checking the element dot type. If the dot type is a text, then call a function that renders text. So since you probably want to render text and checkboxes differently, so they might have different fonts, different styles, different colors. So if you want to render a text, you'll call this function and break. If it's a select box, you'll call this function and break. If it's a checkbox, you'll call this function and break. But you can see how this might be hectic and this code might go on forever. This is terrible. Every single time that we add a new UI element, we have to modify this function. So if I were to add a search, then I'd have to add another case and then search, and then I'd have to create a function that renders search, and then I'd have to break. So this could go on forever. Let's see how we can fix this using polymorphism. We give each class its own unique render method instead of doing all of this. So inside the class itself, so inside our text box, let's say, we give it a render method. And inside the render method, we run all the functions that's necessary for rendering it. So let's just say rendering input field for now. And inside our select, rendering search select field. Now look at how simple our rendering logic becomes. We simply just make a list of elements. So our elements could be a new text box and a new select. So again, if you don't understand what I'm doing here, then you need to go back and polish on your classes and objects. And we simply just loop over them. Elements. As soon as we loop over them, we simply just called element.render. And that's it. So we created a constant elements, passed in all the elements that we needed to render, loop through each element, and simply call their render method. Since every element has its own render method, you don't need to go around checking what kind of element it is and then calling a render method respective to that element, which is a different function. We don't care what type of element it is, each object knows exactly how to render itself. That's called polymorphism. So, to summarize our video today, it might have been a lot, and since this is an advanced JavaScript roadmap, we assume that you have some prior knowledge to JavaScript, and classes and objects should be a given. So, first we learned about encapsulation. It basically reduces complexity by grouping related variables and functions together. Next, we got abstraction, which reduces impact of change by hiding internal details. So things that a developer does not need to change or a developer doesn't need to have access to are hidden. Next, we have inheritance, which eliminates redundant code by sharing properties. So we looked at the super and the extends keyword. Finally, we have polymorphism, which might have been a little complex, but make sure to come back to this video, replay through a few times. It basically refactors ugly switch case statements by allowing different objects to behave differently, giving them their own properties. So, to recap, encapsulation groups related variables, abstraction hides details, inheritance eliminates redundant code, and polymorphism helps us get rid of long if else or switch statements. In the next episode, we're going to stop talking theory and start writing code. So we will look at how to create objects using factories and constructors. I'll see you there. This is the second episode of Advanced JavaScript, and in the last lecture, we learned how to use object literal syntax to create an object. But there is the tiny problem here. Imagine you learned how to create object literal syntax. Imagine you want to create two circle objects. You copy the code, you paste it. Now you have duplicated the implementation of the draw method. If there's a bug in this method, you have to fix it in multiple places. In the last lecture, you learned how to use the object literal syntax to create an object. But there's the tiny problem here. Imagine you want to create two circle objects. You copy the code, you paste it. Now you have duplicated the implementation of the draw method. If there's a bug in this method, you have to fix it in multiple places. This is the maintenance nightmare. To solve this, we use factory functions. Just like a real factory produces products, these functions produce objects. We define a function and call it create circle. So to define a function, start with your function keyword and create circle. Notice the naming convention. This is camel notation. The first letter has to be lowercase. So to create a circle, we'll probably need a radius, right? Take a radius, and inside we simply return an object. So to return an object, type return, and either you can create an object, suppose circle, and add some properties and then return circle. Or why do all this redundant code when you can simply just return an object like this? So this would return an empty object. Now we're editing inside the object. In modern JavaScript, if the key and value pairs are the same, then we can remove the noise. So instead of typing radius, radius, we simply just type radius once. So it means the same thing, but it's a lot cleaner. And for methods, we don't need the function keyword anymore. So instead of typing function draw, you don't need the function keyword anymore. Simply just use the shorthand syntax and type in draw. So we're simply going to log console log draw. And now to create a circle, so this function would probably have your logic on how to create a circle or do a certain task. To create a circle, we simply call the factory function. So circle1 equals to create circle with a radius of 1. If you need another one, simply copy and paste and name it circle2, let's say with the radius of 5. We've defined our logic in one place. If we fix a bug in the factory, so if you have a bug in your draw method, if you fix it here, you fix it in all places for all of these circles. So we've created the circle. What can we do with the circle? So we can console log a bunch of things. So circle1 dot radius is something that we can console log, and it should be 1. We can call the draw method, and it'll simply just print draw. So simply just print draw. And of course, you can call the draw method itself. Now there's another pattern called constructor functions. This is familiar to developers coming from C# or Java. The naming convention here is different. We use Pascal notation. The first letter of every word should be uppercase. So I can name a function circle, and inside I pass in the radius. Here, we don't actually return an object. Instead, we use the this keyword. Again, the this keyword refers to the object executing this code. So this dot radius equals to radius. What does this do? Think of this as a reference to a new object that we're creating. We are setting the radius property on it. We do the same for methods. So this dot draw equals to function console log draw. Now to create an object, we use a new operator. So const another circle equals to new circle. Notice that we use the new keyword. The new keyword simply calls this function, and inside this function, it takes in a radius and it creates a draw function. So this dot radius refers to the radius of this object. So another circle is an object. Object has properties. So another circle dot radius would simply just create an object, another circle, and set its radius to something. Set its radius to something. So this dot radius simply means another circle dot radius, because another circle is calling the new circle, and it equals to the radius that we have passed in as an argument. So the radius that we passed in as an argument is 1. This dot draw is simply adds a draw method to our circle, and the draw method is a function that simply just does this. So an object is created in this way. If I copy pasted this code and created a circle with, let's say, a radius of 10, another circle 2. So another circle 2 would look something like this. First of all, this dot radius runs equals to radius that we passed in as an argument. So this dot radius is another circle dot radius, and it passes an argument of 10, so it creates 10. Then this dot draw function runs, and this dot draw function creates a new method inside the object called the draw method and sets it to that. Alright, this is the most important part. This is also the part that confuses many beginners when we use the new operator. Again, let me see. There are three things that happen under the hood. First, it creates a brand new empty object. Second, it sets the keyword this to point to this brand new object. That is why this dot radius works. So it points to the object and it creates a property inside the object and equals it to the value that we pass in. So radius is simply the argument that we passed in over here, which equals to 1. Third, it automatically returns this object from the function. So the object is created here and it automatically returns it and assigns it to another circle. So first it creates an empty object, creates some properties, and then assigns this empty object to our another circle. Think about this. If you forget the new keyword, this will point to the global object, the window, which is a disaster. So don't forget the new keyword. The new keyword makes sure that the object created here points to another circle. One last thing. In JavaScript, objects are dynamic. Even after we create them, we can add or remove properties. We can add a location property on the fly. So another circle dot location. You can simply just add a property by doing this. Or we can access properties using bracket notation, which is useful if property names are dynamic. So another circle, location. So both of these are valid. We can even delete properties using the delete operator. This is useful when sending data to a client and you want to remove sensitive info like passwords. So you can simply just delete data by referring to them like this. So you might be asking, which pattern should I use? Both patterns are equally good, but constructor functions are standard if you come from a class-based language. Factory functions are arguably simpler because you don't deal with this or new. My advice, don't get hung up on the debate, pick one pattern, stick to it, and be consistent. In the next episode, we're going to look at prototypes and see how we can optimize our constructor functions to save memory. See you there. Hello and welcome back. We've learned how to create objects using factories and constructors. But if we stop there, we're leaving a massive memory leak in our application. Today we're going to look at the hidden link that makes JavaScript one of the most memory efficient languages when handled correctly. The prototype learns how to create objects using factories and constructors. But if we leave there, we're leaving a massive memory leak in our application. Today we're going to look at the hidden link that makes JavaScript one of the most memory efficient languages when handled correctly, the prototype. In episode 2, we put the draw method directly inside our constructor. That works fine for 1 or 2 objects, but imagine an app with 1,000 circles or 10,000 circles. Each circle would carry its own copy of the draw function. That's 1,000 copies of the exact same code sitting in memory. It's like buying 1,000 cars and insisting each one comes with its own private mechanic in the trunk. It's a waste. Let's start by creating our function all over again. So we're going to create a function, circle, which obviously takes in a radius property, and we're setting its radius to the radius that the user supplies and its move to a function that simply just moves the object. In this case, I'll just print out move. So these are called instance members. Instance members are unique to each object. Next, we have something called prototype members. This time around, we're going to introduce something called prototype members. These are shared by all objects and we use the dot prototype property of the constructor. So circle dot prototype dot draw equals to function console log, just console log draw. And we can create 2 circles. So new circle and const c2 new circle. So we looked at how new objects are made using factory constructors in the last episode. Now, C1 and C2 actually stores only the radius and move method locally, but they both have access to this draw method through their prototype. If we have 1,000 circles, there is still only one draw method in function memory. However, there will be 1,000 different radius and 1,000 different moves. When you access a property or method, JavaScript doesn't just look at the object. If it doesn't find it there, it looks in the prototype. If it's not there, it looks at the prototype's prototype. This is called the prototype chain. It's like a corporate ladder. If the clerk does not know the answer, they ask the manager. If the manager doesn't know, they ask the CEO. This is the part that trips up everyone, the constructor and the instance. Circle.prototype is what the constructor has. It has the blueprint for future objects. C1 proto is what the instance has. It has the actual link to the blueprint. Basically, C1 dot prototype is actually equal to circle.prototype. In modern code, we use object. So we use object.get prototype of C1 instead of using this notation. But they point to the exact same thing. You can easily mix and match these things. An instance method can call a prototype method and vice versa, because they are all part of the same context when executed. The this keyword still points to the exact same object that started the call. So what that basically means is inside our draw function, I can still call the this.radius because this.radius is an instance member and this is still available to us inside the prototype chain. If I have another prototype, circle.prototype.toString, which would also be a function, let's just return something. So let's return circle with radius, this dot radius. So again, this dot radius is available to us inside the prototype because it's an instance member. Let's look at the summary. Storage. In an instance member, the storage is on the object itself. On a prototype member, it's on the prototype object. Memory. Every instance member is multiplied per object. So if you have 1,000 circles, you'll have 1,000 different radii to go with those circles. Prototype members are only one for every object. So any object that you create with that function will have only one copy of that prototype member. Use case. If you want unique data, like every circle needs to have a unique radius, it might have a unique circle, it might have a unique background color, a unique border width, a border radius. So for those reasons, you use instance members. So using this keyword. If they have shared behavior, so if you're drawing the circle or rendering the circle on the screen using the same property or same behavior, or if you want a bunch of circles to have the same behavior when clicked on or hovered upon, then you use prototype members because they share the exact same behavior while taking only one space in the memory. Prototypes are actually how JavaScript achieves inheritance without the overhead of massive memory usage. By moving our methods into prototype, we made our code professional and scalable. But we've only seen how one type of object shares its own methods. What if we want a square to inherit everything from a shape? That is a whole different level of prototype chain. In the next episode, we're going to be looking at prototypal versus classical inheritance. See you there. Welcome back to episode 4. We learned how to put our methods on the prototype. Great. But look at this. Both our circle and our square need a duplicate method and a color property. If we have to write that code twice, we failed the dry principle. Don't repeat yourself. We need a parent that both can learn from. So let's jump to our VS Code. Let's start by creating a parent constructor. So a function called shape that has a color. Inside it, we use the this property to define its color that the user provides. Then we have a prototype method, which is shared across all objects, called duplicate. And what it basically does is it just for now prints duplicating this dot color shape. This is our library. An object that links to this will instantly know how to have a color and how to duplicate itself. So every object that we make will have its own unique color but share the same duplicate property. Now when we make a circle, we want it to have its own radius, but we want the shape to handle the color. We use the shape.call. Think of this as borrowing the shape constructor for a moment to set up our new object. So let's create a function, circle. Our circle obviously has a radius and it has a color. Inside it, we use something called a super call. What we do is we pass this so that shape adds color to our new circle. So shape.call, we pass in this. So we're passing in this and we're passing in color. And we're setting our radius to the radius passed in by the user, or passed in when we call this function. This is the most important line in prototypal inheritance. By default, circle.prototype inherits from object.prototype. We need to rewire it to inherit from the shape.prototype instead. Since circle.prototype doesn't really exist right now, we need it to inherit from shape.prototype. So to do that, we simply first we need to call circle.prototype, and we create an object. We create a shape prototype. And we need to actually reset this constructor. Why do we need to reset this constructor? We do this by circle.prototype.constructor equals to circle. So when we do object.create, the constructor gets wiped out. So to reset the constructor, we actually need to run this so that the constructor goes back to its normal form. And now we can circle.prototype.draw function drawing circle. With object.create, we basically tell JavaScript, if you can't find a method on circle, go look in the shape library. We also reset the constructor because object.create makes the circle think that it was made by a shape, but it's not. We need to remind it who its real parent is. So we can start creating new circles by simply creating new circles. We can start creating new circles using const c1 and a new circle. The first argument is our radius. Our second argument is red. Then we have access to c1.draw. We have access to c1.duplicate. So if we simply just log our c1 and run this. So drawing circle, duplicating red shape, and this is what our c1 looks like. This drawing circle is a direct prototype of our circle. So circle.prototype.draw, which is a drawing a circle. But duplicating red shape is a prototype of shape that circle inherits because we used all of this code. In the end, our circle object has two properties, color and a radius. In the end, our circle has two properties, color and radius. We define radius here itself, but the color is coming from a super call to the shape function. So we're calling in shape, which sets our color for us. So if we didn't call this function, and we simply ran this, then we wouldn't have that color. And it would be undefined because we never called the super function to set our color for us. Why do we need this? Because you can have other shapes instead of a circle. So you could have a triangle. triangle would likely not have a radius, it would have a height, it would have a base, and it would have a color. So to simply set its color, shape.call this.color. Our shape would set its color. So shape has all the default properties that every single shape should have. So it could be color, it could be this dot border radius equals to radius. So in which case it would take color and it would take radius, and simply we would also take color and radius and color and radius, and we would shape.call. Inside our shape.call we would also pass in our radius. We also need to pass in our this so that it knows who to assign it to, and you could simply just height this dot height equals to height, and this dot base equals to base. Oh, seems like we repeated radius here, so let me just name this as border. Okay, so this dot border is actually equals to border. And we can create a new object for our triangle by calling t1 new triangle, which takes in a height, base, color, and radius. So height of 10, base of a height of 10, a base of 2, color of red, and a border radius of 2. Now, if we simply copy this and paste it for our T1, and run it, we need our draw prototype for our triangle as well. And we need to create a prototype so that our triangle inherits from our object. So triangle, triangle. And if we run this, then we're drawing a circle, we're duplicating its red shape, and our circle has a color, a border radius, and a border. This is our summary for today. Calling the parent is simply just parent.call, passing in this and all the arguments that parent requires. The parent for a circle is shape. Parent for triangle would also be shape. Simply, you can think of parents for other things. Like if you had a big box and you had a smaller box inside it, the parent for that smaller box would be the bigger box. Then you have linking prototypes. So to link prototypes, you link the child prototype to the parent prototype by simply child.prototype equals to object.create parent.prototype. So if parent has a prototype method that the child needs to access, you link it using this statement. Lastly, you need to reset the constructor. You need to reset the constructor because child actually forgets who created it. It makes the child think that it was made by the parent, but we need to remind it who its real parent is. You now understand the old masters of JavaScript and how they built complex systems. This foundation is what makes modern classes possible. But how does the computer actually keep track of all these function calls and this context? To truly master the language, we actually have to look under the hood and understand what a call stack is. In the next module, we start engine room. We'll start with the execution context and call stack to see how JavaScript executes your code line by line.
Welcome back to another episode. This is episode 5 of Advanced JavaScript. And welcome to the engine room. We've spent module 1 building complex projects, but now we're lifting the hood. And if you've ever wondered how JavaScript decides which line of code to run next, or why a function remembers its variables and such, this is where we'll explain all of that. We'll start off this module by talking about the execution context and the call stack. JavaScript is a single-threaded language. Now, that may be complicated to hear, but it basically means that it cannot run two things at the same time. It runs only one piece of code at the same time, but how does it remember what it's running? Think of execution context as a container where the code is currently being evaluated. Whenever you run a script, JavaScript creates the global execution context, which has two phases: the creation phase
and the execution phase. So JavaScript is like a chef with only one burner and one knife. To keep track of what needs to be cooked and in what order, he makes use of a to-do list. In JavaScript, that is called the call stack, and the environment the chef is working on is called the execution context. So this is the global execution context, which has a memory component and a code component. So the code component is actually what you type, the main thread of the execution. So you have your functions and everything. And memory component are all your variables. So all the values you're storing inside the browser is your memory component. The way the call stack works is in a last in, first out basis. It is a mechanism the engine uses to keep track of its place in a script that calls multiple functions. It's like a stack of Pringles. The last chip you put in is the first one you eat. When you call a function, a new execution context is pushed onto the stack. When the function finishes, it is popped off. Again, this is called last in, first out. So like a stack of books, the last book that you put onto the pile is the first book you have to take out. Alright, let's look at this in VS Code. Let's start by creating a variable called name. So code it. Let's create a few functions here to look at how call stacks work. So I'll create a function called greet, and inside greet, I'm simply just going to log hello. I'll create another function called respond, and inside this function, I'm going to simply log how are you doing. I'm going to call the greet function, and I will call the respond function. So if I run this in my terminal right now, you'll get hello, how are you doing? Because greet is calling its function and respond is calling its function. Now I'll simply just move this respond into the greet. What do you expect would happen? The same thing. But JavaScript runs those two things differently. Now let's look at how this actually looks in a call stack environment. Let's trace it in our minds first. Greet. Greet calls the greet function. So the call stack has the greet function added onto its top. Then it logs hello. Then inside it, there is the respond function. So the respond function gets added to the call stack. Then you have a respond function. Inside the respond function, it prints out how are you doing, and the function is finished. So respond function is now removed from the top of the call stack. After respond finishes, greet function has also ended, so greet function is now removed from the call stack, and we've ended the call stack. So now we're in the global context again. Let's look at how this actually looks like. Let's look at how this actually looks like. So for that, I'll simply create a file called index.html, and inside it, I'll create a boilerplate code, and I will link my JavaScript. So the way you link JavaScript is simply like so. Oops. Simply like so. Save it, and we will go live. So you won't see anything because it's a white screen. I haven't added anything. So let me just add a paragraph tag and say hello coding, just to make sure. All right. You see hello coding here. Let's open up the console. So you can either right click and open your console by clicking inspect, or simply just press Ctrl Shift C or Ctrl Shift I. So I have an option called debugger here. If you're on Chrome, then you'll have something called sources. So I'll go into my debugger. So I'm inside my debugger, then I can see my script.js. I can see my index, HTML, I can see everything else, and I can see my script.js. Inside this script.js, if you move your attention to the right side of your screen, you'll see a bunch of things. So you have breakpoints, watch expressions, and all of this. So what a breakpoint basically is that right now the code runs synchronously. So all of this code is running at once and it's finished. So this script is finished and we're logging hello, how are you doing in the console. Putting a breakpoint basically means that when the execution reaches this step, I want you to stop. So let's stop at greet. So when we reach this greet line, so when we're calling greet, I want you to stop the execution. So I've added a breakpoint by simply clicking on the number here, and now I'll refresh the page. So once I refresh the page, a few things will happen. It'll show that the debugger has been paused, and it will show that it has been paused on the breakpoint. And another thing will appear called call stack. We have the global environment in the call stack. So global is basically your window. If I move into the call stack, so I can click on step in right over here, then greet gets added to the call stack because the greet function has just been called. So the greet function is added to the call stack. Now before I can move back to my global, I have to finish my greet. Inside greet, you can see that the pointer has moved to console.log hello. If I move in again, I'll reach the respond. So console.log hello gets executed, then I move to respond. If I move in, respond is called, so I move into the function respond, and you can see that respond has been added to the call stack. Now again, if I need to get back to greet, respond has to finish first. If I step in again, console.log how are you doing has been executed, and the respond function now finishes. Now the next time I move in, respond will be called off the call stack because respond has finished executing. So as you can see, respond gets removed from the call stack. Now we have greet left, and we've reached the end of greet because respond has executed. We've reached the end of greet. So now greet gets called off the call stack. So greet gets removed off the call stack, and we end the program, and it's finished. So this basically shows you how call stacks work, and it is the last in, first out principle. So the thing that gets added on the last has to be taken out first. So whatever is on the top needs to be taken out first for the things on the bottom to be taken out or accessed. Let's come back to our code here. Before the first line of code even runs, JavaScript actually allocates memory. It sees a function declaration and it stores the whole function declaration using a memory. This creation phase behavior is exactly why hoisting happens, which we will cover in detail in the next episode. For now, just remember that memory is set up before the code runs. What happens if a function calls itself forever? So if a function just continues calling itself over and over again, will it just get added to the call stack indefinitely? This is called recursion without an exit. So the stack keeps growing until it runs out of space. You've probably seen this error called maximum call stack size exceeded. This is literally what stack overflow means because you've asked the chef to do a million things at once without finishing any of them. So let's recreate what a stack overflow would look like. Let me remove the second function. Inside the first function, we called greet, we console log hello, and let's just call itself again. So recursion is when a function calls itself. A proper way to do a recursion would be to give it a condition, which we call a base condition. So if condition, then if, let's say true, then continue with recursion. Obviously, you wouldn't have a base condition that's always true, but if a condition has been met, you will recurse. But what happens if you create a recursion that doesn't have a base condition and it just infinitely loops? So greet has been called, it will log hello, and it will call itself over and over again. Let's look at this in the browser console. So if I refresh this page, now if I go into my debugger, I go into my console, it says internal error, too much recursion. So it simply tells me that recursion has happened way too many times. You can also click on learn more to look at this, which basically says maximum call size exceeded, which you'll get in Chrome, too much recursion, which you'll get in Firefox, and maximum call size exceeded, which you'll get in Safari. So this happens when a recursive function runs infinite number of times. So I'm sure there's a set number of times that it cannot run beyond, but basically if any of your conditions are infinitely recurring or recursing without base conditions, you'll get a maximum call size exceeded error, or you'll get a too much recursion error. So the summary of today. You have your global execution context, which gets created when the script starts. So it's the base of your call stack. Then you have your function execution context, which gets created every time a function is invoked. So every time you add something to a function, or every time you're calling a function, it gets invoked. Third, you have your call stack, which manages the order of execution. So it's last in, first out. Then you have your two phases, which is the creation phase and the execution phase. We looked at the execution phase in detail today and hinted something at the creation phase. Understanding call stack is like knowing the map of a city. Now you basically understand why things happen in the order that they do. It is the foundation for everything that follows, so debugging is much easier when you understand how call stacks work, especially when we get to the event loop later in episode 10. But how does JavaScript find variables within these contexts? What happens if a function looks for a variable that isn't inside it? We'll look at that in the next episode. Hello and welcome back to episode 6 of Advanced JavaScript. In episode 5, we looked at the call stack in action. Now we need to talk about the invisible rules that govern where your variables live and when you're allowed to touch them. If you've ever looked at an undefined variable or a reference error, you're actually now about to find out why. So this episode is all about scope, hoisting, and the TDZ. Before JavaScript executes your code line by line, it performs a creation phase. It scans your script for declarations. This is why some things seem to exist before they are defined. It's not magic, it's just the engine looking at everything that's defined before it runs any functions. Scope defines where a variable is accessible. A global scope is accessible everywhere. Variables created inside a function stay there, which is the function scope. Then you have a block scope, which are variables created inside curly braces like if statements or for loops. Using let or const are locked inside that block. So this is how the scope chain works. So everybody can access the global chain. Some people, so some functions, a limited environment can access the functions variables, and a very, very limited part of your code can access the block variables. Let's come back to our VS Code. So let's look at the execution phase. Let's execute greet first and then define the function greet. So our function greet should just be hello. What would you expect to happen? We called it before we've defined it inside the code, but yet when we run it, we still get hello. This is because the whole function gets added to the memory before running the function, or before executing the function, everything, all the variables get added to the memory. This is why this works. But now what if I try to console log something? So my variable. If I try to log a variable called my variable and define it somewhere below the execution, so if I run this, it will give me a my variable is not defined error. So the name is actually known, but the value of it is not defined yet. And this can be a global variable if I just add the word var, so it'll actually show undefined. So var basically means that this is a global variable. And the program actually knows that a global variable called my variable exists, but there's no value. It hasn't been assigned a value yet because the value is assigned on line 9 and we're accessing it in line 7. That's why it returns undefined. It effectively sees, so what's actually happening here behind the scenes, breakdown one by one, is at the top of the program, the engine actually sees something like this. And it sees this. So what's happening is the variable gets declared at the top. So the engine runs through your entire file, finds all the variables that have been declared and declares them at the top. So this variable is declared, this function is declared at the top. But the value of the variable is actually defined only on line 11, and it's not actually defined before this is hit. Since the variable has already been declared, but not defined yet, so you can actually see that the value is undefined and not just value not found or variable not, and not just variable not found or value not found. Now let's look at the scope chain. Let me remove all this code and let me create a constant user called Alex. Now this is global. This is in a global context because I've defined it outside any variables, because I've defined it outside any functions or any curly braces. Let me create a function called profile. And inside it, I want to declare a variable called action and set its value to coding. So this is a function scope. This is a function scope variable, and this is a global scoped variable. Under it, actually inside the function, then create the if statement. If true, status equals to active. So this is what we call a block scope. And let me do something. And at the end of this if statement, let me do something. Let me console log. I'll console log user is status and action. So what do you think happens here? And what do you think happens if I try to console log the status outside here? So pause this video and think about it for a while. Obviously, you need to call the profile function. So pause this video here and guess what the output would look like. All right, first of all, the user. Let's look at the lookup process for this statement. First of all, it checks for user. So first of all, it checks for user. Now, it's not in the block because it checks for user inside its own immediate block. It's not defined inside this block. So it moves up to function. Is it in the function that it's defined in? It's not in the function. So it moves up to global context. Moves up to global context. Now, is it in the global context? It is. We find the user Alex here, so it pulls the user variable from here and then saves it in user. So what would happen if it found a user here? So if I had a user called Steve, what would it do then? It checks for the user first in the block context. So inside its own block, does it find a user? Yes, it's Steve. So it simply replaces the user with Steve instead of Alex, because it actually never reaches that global context because it immediately finds it in block. Same thing if I place Steve inside my function. It will look inside its block first, doesn't find Steve, it goes inside the function, it finds Steve, and then replaces the user with Steve. All right. Next, we're going to check for status. It checks inside its block first. It finds the status in block, so found in block. Simple as that. Next, it checks for action. First of all, not in block, because it doesn't find it inside its immediate block. So it moves up to function. Moves up to function. Does it find it here? Yes, it does. There's a variable called action inside its function. So that's how this statement actually finds all of its variables. Now let's look at this. Now VS Code already gives you an error that it cannot find this. So let's actually look at the lookup process for this. So checks for status. Does it find status in its immediate block scope? So you have to now remember that its immediate block scope is the curly braces that it is defined inside. Which set of curly braces is this console log statement defined inside? It's this curly brace and this curly brace. So if you look at this, the if statement is its own curly braces. And the if statement's curly braces start here and end here. So this is the block scope for if statement. But our console log is actually outside this if statement. So it is as if this if was not here at all. It's actually defined inside this block context. So something about block context that you have to remember is that one block context that is on the outside cannot access variables inside a block context that is in a block context that is inside it. So the outer block context cannot look at the variables inside the inner block context. It actually does not find status. It does not look inside the block context over here. It just looks at its own set of parentheses. Does it find status here? It does not. So checks for status, not found, because it is actually locked inside the if block. This statement cannot look inside the if block. This statement can only look inside the function block. Next, we'll just call in profile. So if we run this program, we'll get Alex is active in coding because it finds all three of these variables. But console log status returns an error, status not defined, because it actually never finds status in the first place. Now that we understand how scope chains work, so the upward searching mechanism of JavaScript, let's look at the TDZ. Now, what is the TDZ? Suppose I console logged age, and then in the same statement, defined age as 25. What would happen? If I run this program, I would simply get cannot access age before initialization because it has not been initialized yet. But if I console log age in the next line again and run it, so this is what we call a TDZ. The TDZ, or temporal dead zone, so a temporal dead zone, is the period between the start of the scope and the actual line where the variable is declared. So if this were the case, everything between this is a temporal dead zone. So all of this is a temporal dead zone because it's the start of the context until the actual variable is defined. And anywhere inside the temporal dead zone, if you try to access the variable, or if you try to access them in this zone, JavaScript throws something called a reference error. It's the engine's way of forcing you to write cleaner code because you're trying to access something before it's initialized. So let's do an example of this. Let me start with curly braces so that you know that this is a block. Inside it, I'll console log price. Simply, if I try to run this now, I'll get a reference error. Price is not defined, a reference error. And let price equals to 100. So still get a reference error because cannot access price before initialization. So this is actually a temporal dead zone. I cannot access the price anywhere inside here. But if I console log price after this, as soon as I declare this variable, the temporal dead zone ends. The temporal dead zone for price starts here. This gives a reference error, and the temporal dead zone ends for right here. And the temporal dead zone ends for price here. And here, this simply just works. If I run this code, and it works here. So if I run this code, I'll still just get a reference error because the way that this plugin is set up actually just exits as soon as it encounters a fatal error like this. So if I comment out this code, or just cut this code completely and then run it, I'll get 100. So this works because there's no temporal dead zone. But if I cut this out, then I get a reference error. All right, so the summary is always use const unless you know the value will change. So this is a pretty basic, well-known thing. Next is never use var, because in modern JavaScript, you rarely use var. Var is used for declaring global context. So even if you declare a variable inside a block or inside a function like we did earlier, but you use the keyword var, then it would be accessible outside that block or outside that function. And it just makes a whole big mess. In modern JavaScript, we don't code this way. Also, declare variables at the top. So to avoid the temporal dead zone, you always declare variables before they're actually accessed or they're initialized. So always declare your variables at the top. Keep scope small. You don't want a lot of variables to be inside the same scope. So keep different segmented scopes small. And that's all. So mastering scope and hoisting is actually really important because you actually become a developer who can accurately debug and know the code that they're writing instead of just guessing around what the variables or the declarations that they do will throw an error. Now you'll actually understand where your variables are and why they behave the way that they do in case they throw an error. But there's one more thing related to scope. What if a function could remember its scope even after the outer function has finished running? That is not a bug, it's something called a closure. And it's actually the secret behind the module pattern in advanced JavaScript. So we'll look at that in the next episode. Welcome back to episode 7 of Advanced JavaScript. In the last episode, we learned about the scope chain. It's how a function can look up to find variables. Today, we're looking at what happens when the function leaves home but still remembers where it came from. This is called closures, the single most powerful concept in JavaScript. A closure is not a special object you create. It's a natural byproduct of how JavaScript works. When a function is declared inside another function, it gains the access to outer function's variables. But even after the outer function has finished executing and popped off the call stack, the inner function still carries those variables around in a backpack. This backpack is called the closure. So let's start by creating a function. So create a counter. Inside this function, I want a variable called count to simply just be 0. This variable, you could say, lives inside this closure. Then inside this variable, inside this function, we're actually just going to return another function. So when I call this function, I just wanted to return another function. And what this will do is basically increase the count by 1 and then console logs the current count. So current count is simply just count. Const increment equals to create counter. So I'm calling the counter function and storing it in the variable increment. All right, let's run this program actually. So this variable lives inside this closure, which is the bigger function. So the function that's on the outside, the outer function. We actually return this function to the outside world. So when the create counter function is called, this function is returned to the global context. What it does is it remembers count from its birthplace. So its birthplace is inside this function, so it remembers the value of count over here. So it remembers that count was 0 and that it has increased count by 1 by count plus plus. And console log simply just prints its count. All right, when we do this, what happens at first? So create counter function has finished running. Normally, count should be dead. So whenever a function finishes running, so this function finishes running, then all the variables at the end of the function get removed from the memory. So this function should essentially be dead. So the value of count should actually just disappear. Now I'll demonstrate this by another example. So if I actually just create a function called greet and then say greeting, const greeting equals to hello, and I call the greet function. So I call the greet function and then try to print greeting. So what would happen? I actually get greeting is not defined, a reference error. Even though I clearly defined greeting and called the greet function to create the variable greeting, I cannot access it outside this function. Because once the execution of this function has finished, I can no longer access the variable inside it. The variable is essentially dead. So that's what I'm saying here. Normally, this count variable should be dead after the create counter finish has running. After the create counter function has finished running. But if I call increment, now remember increment is just the create counter function, the output of the create counter function. So increment is actually this function here. The create counter function runs, it returns a function, and this function gets stored in increment. So increment is actually just this function. Notice if I run this program, I actually get current count 1. But what's interesting is if I run increment again, I'll get current count 1, current count 2. So notice that create counter is called and it finishes executing on line 9. Yet, when we call the increment, it still knows what count is. It didn't just remember the value. It has a live link to this variable here. This is called a closure. But even though the function has finished running, this inner function actually still has access to the value of the variable of count. Why do we care about this phenomenon? Although it may seem like a bug, this is actually a feature called closure. So make sure that you remember how this works. So why do we need it? In languages like Java or C Sharp, you have the private keyword. In older JavaScript, we didn't actually have a private keyword. We used closures to hide data. If a variable is inside a closure, it is physically impossible for the outside world to touch it unless we provide a specific function to do so. This is the foundation of module pattern. So if you look at this function here, it is physically impossible to access the value of count unless we access it via the increment function that we provided access to. So if we didn't provide access to this function, then this count would physically be impossible to access outside this function. But since we provided an entry point, we can access this count variable. So let's transition to a more complex VS Code example. So let me create, you can skip this part if it's all getting a bit too complex, or you can rewatch this video a couple of times, but I will be giving you a live demonstration of how closure works and not just a kid's version of it. All right, let me create a constant bank account and I will assign a function to it. But inside its parameter, I'm actually going to feed it another function. So this is a higher order function. And inside this, I want a couple of private members. So in my bank, I want a couple of private members that should not be able to be accessed from the outside. All right, so their balance is 0. So this balance should not be able to be accessed by outside. I'll create a function called validate amount, which takes an amount and simply just returns if amount is greater than 0. So if the amount is greater than 0, the account is valid. Then I'll have a public interface. So we only return what we want the world to see. So we don't want to return all the details, we just want to return what we want the world to see. So we return a function, deposit amount, if validate amount balance plus equals to amount, and simply just log deposited amount balance. I'll return another function called withdraw amount. So inside this withdraw amount, if amount is smaller or equals to the balance, then balance minus equals to amount, and we'll simply just console log withdrew amount, balance is now balance, and this should be small braces. So this is what we call the immediately invoking function. So this function will get invoked as soon as it runs. So what's actually happening in here? I can access functions inside the bank account. So bank account dot deposit 100 would give me access to the deposit function inside the bank account. All right, let's look at this from the top. we created a variable called bank account. Inside bank account, we create the immediately invoking function that returns two different functions. So it's a function that has its own functional scope, right? Inside its functional scope, we have balance, we have a function that validates the amount. But these two things are things that we don't want the outside world to see. So we don't want the outside world to immediately be able to access the balance or immediately be able to access the validate amount code or anything else that we put in here. So they might have customer names like John. So you don't want the outside world to be able to access names like John. So what do? We create a public interface. Now to create a public interface, we're simply just returning two functions to this constant. So bank account, we're returning two functions to bank account. Now bank account actually holds these two functions. Bank account also holds these values, but these values cannot be accessed from the outside world. What are these two methods? Since these two methods exist inside the original function, so these functions can access balance and return amount. These functions can access balance variable and validate amount function, but nothing else can actually access these two things directly. So if you want to access balance and validate amount, we can only do it via these two functions. Obviously, these two functions don't have a print statement that simply just prints the balance, right? Or that simply just prints sensitive information like PIN or ID, like PIN or ID. So like you might have customer pins in here. So you might have customer pin, something like this. And you could have a function that checked if the pin was valid or not before you withdraw amount. So if this and if and you could create a nested if statement that checked if pin is valid. But you don't want this pin to be accessed by the outside world. So the deposit amount, so the deposit function takes an amount argument. So if you give it an amount, it checks if that amount is validated. The validate amount calls this function. This function either returns true or false. It returns true if the amount is greater than 0. It returns false if anything else. If it's valid, then it adds that amount to the balance and then prints the deposited statement. With the withdraw amount function, the amount is taken by an argument. Then it checks if that amount is smaller than the balance. If it's smaller, then it's valid. It deducts that amount and prints the balance. So doing that, you can now actually access the deposit function directly of the account variable. You cannot actually access bank account.balance. So if you simply try to console log this, bank account.balance, you wouldn't be able to see that balance. It's undefined because this balance is actually not returned. It exists inside the function, but the only value that is returned to the bank account variable is these two functions. These values are not returned, they just exist. But what you can access is bank account.deposit. So bank account.deposit 100. So if you ran this, then deposited 100, balance is now 100. If we ran the statement a couple of times, deposit 100, 100, 200, 300. So it's actually remembering the balance from the previous times and not just spouting out nonsense. You can actually withdraw amount now, bank account dot withdraw 200. And it deposits 3 times and then withdrew 200 at once and deducted 20 according to this logic here correspondingly. And you cannot access these variables, you can only access the returned ones. This is a professional pattern. This is what's called a black box where balance and validate amount logic are completely hidden. You'll see this everywhere in library development. In episode 9, we'll actually look at how modern ES6 classes handle this with something called private fields. But understanding closures is still mandatory for senior level of debugging. One small warning though, closure prevents variables from being garbage collected. So these variables won't be garbage collected. If you create thousands of closures that hold on to massive objects like arrays that you no longer need, you can cause a memory leak. Use them wisely, only hold on to what you actually need. Usually, garbage collection would remove all these variables from memory as soon as this function ends. But since we're using closures, so we're using functions that access this even after the execution of this main function has ended, these won't be garbage collected, or these won't be removed from memory. Make sure that you're only using ones that you need and you don't have large arrays stored in memory, otherwise you'll cause a memory leak. So that was all for closures. They basically allow us to encapsulate logic and maintain state without polluting global scope. But there's one final piece of the engine room. What do we call functions? When we call these functions, who exactly does the keyword this refer to? When we call these functions, who exactly does the keyword this refer to? Is it the object, the window, or the button that we clicked? Now it's finally time to tackle the most confusing keyword in this language, the this keyword. We'll move on to the next episode. See you then. With episode 8 of Advanced JavaScript. In this episode, we'll be talking about the this keyword, call, apply, and bind. Who is this? If you have ever written JavaScript for more than a few weeks, you probably have been frustrated by this keyword. It seems to constantly change what it points to. Sometimes it points to your object, sometimes it points to a window, and sometimes it's just completely undefined. Today we're going to demystify. The golden rule that you must memorize is the value of this is determined by how a function is called and not where it is written. Again, it's determined by how a function is called and not where it's written. Let's look at some examples. So the two most basic rules. First, if a function is part of an object, we call it a method. In a method, this refers to the object itself. So if I create an object called video, so this is an object. Inside the object, I have a few properties. So advanced JavaScript could be a title. And I have a function inside it. Now, according to modern ES6 standards, you don't need to define function with the function keyword. You can directly define it in this shorthand syntax. And this function, since it's inside an object, it's called a method. I have console log. I'm simply console logging this. When we call video.play, so play is a function or a method inside the video object. So I can use the dot notation to access it. If I run this, title advanced JavaScript, play function play. What do we get? It simply prints the video object as a whole. So this would be the same as console logging video. The exact same thing. But let's look at this. But if I have a regular function, so if I have a regular function called play video, and it also logs this, and if I call the function, it prints the global object. So object global, it prints the global object. So why does this keyword inside this method reference the object, but the this keyword inside the function reference the global context or the window? It's actually because the this keyword essentially just points to the object that is calling it, or points to the window that is calling it. Since we're calling video.play, the object that is calling this method is video. So the this keyword references to the object calling the method. Whereas when we call the function play video, the object or the window calling it is our global window. So the global window is referred to by this. Now let's look at some common traps that developers fall into at the beginning. So we have our video object as we do. We have our title, JavaScript, and we have our tags. So obviously a video could have tags. It could have tags like coding, web, and front end. All right. We could have different methods inside it. I'll make a method called show tags, and inside this method, this dot tags dot for each. For each is a higher order function. Function. I'll take tag as an argument. I'll take tag as an argument, and I will just log this dot title tag. All right. Basically, what I expect from this output is to get JavaScript coding, JavaScript web, and JavaScript frontend. If I run it, oh, I actually have to call it. So video.showTags. If I call that method, I get undefined coding, undefined web, and undefined frontend. Why is this the case? I expected JavaScript coding, JavaScript web, and JavaScript frontend because let's look at this. This dot tags dot for each. So this, as I told you before, references the object calling the method. The object calling the method is video. So this is simply just video. Video.tags is this array here. And dot for each function basically loops through each and every item and prints it. So loops through each and every item, places it in the tag argument, passes it into the tag argument, and console logs this dot title, which is JavaScript, and the tag that it found from for each. But although we're getting the tag, which is coding, web, and frontend, we're not getting this dot title. It returns undefined. Why is that the case? Because the callback function inside the for each is just a regular function. So this is a regular function. It's not a method of the video object. Show tags is a method of the video object, but this function is not a method of the video object. It is being executed by the for each method. So since show tags was being executed by the video, that's why this refers to video. But this function is being executed by for each. So that this keyword refers to for each and not the video object. And for each dot title simply doesn't exist. And remember rule number 2. A regular function call points to the window object. So this is a regular function call. It points to the window object. The window object does not have a title property, so we get undefined. If you look at this, window object has a few properties. So it has global, clear immediate, set immediate, and all of these properties, but there's no title property. That's why we get undefined. In JavaScript, functions are objects. Everything is an object in JavaScript. That means that they have their own methods. 3 of these methods allow us to explicitly change the value of this, which is called call, apply, and bind. Let's take a simple function. Function play that takes in 2 arguments, a, b, and simply just logs this. All right. With dot call, the first argument is what you want this to point to. The rest are your normal arguments. So play dot call, you can provide an object that you want this to call to. So my object could be named coded, and then you pass in the a and b. If you run this program, you get coded. So the first argument that you pass in into the dot call is the object that will be referred to when you reference this. If you didn't have this, so if you call this, if you call the function without the dot call and just normally, then this would refer to the global object. But since you passed in an object using the dot call function, using the dot call method, it references this object right here. So this keyword references to the object that we passed in. Now dot call is just a method. Play is a function by default, yes, but it inherits some properties from JavaScript. So it inherits properties and methods that already exist from JavaScript. And dot call is just one of those methods. The dot call method takes in 3 arguments. The first argument is an object, and the other arguments are the arguments of the function itself, so a and b. The object argument that we passed into the dot call method is what the this keyword will refer to inside the function. Dot apply is exactly the same. So let me comment this out. Dot apply does the exact same thing, but instead, so I'll just show you name, colon, but instead of passing in the arguments as is, you'll pass in the arguments in an array, and it will do the exact same thing. But the most useful one for our callback problem is the dot bind. Bind does not execute the function, it returns a new function with this permanently set to whatever we pass it. So let's go back to our code. So let's make our video object again. We had our video object, and inside it, we had a title, and we had a few tags, and we had a method, let's say play, and inside the play method, this dot tags dot for each function tag, and we simply just log this dot title, comma, tags or tag. All right, let's look at this function and let's see how we can apply the dot bind to fix the error of us getting undefined. So right now, if I call video dot play, I'll still be getting undefined coding, undefined web. Let's see how we can fix this problem. So to fix this, we can chain dot bind this to the end of our callback function. So the end of our callback function is right here. Dot bind this. So what does this do? If I run the program now, I get JavaScript coding and JavaScript web. What this does is we actually just bind this, which is the video object. So we bind the video object to the callback. Because dot bind this is called inside a method, so it is not called inside the for each. The function exists inside for each, but this dot bind this exists inside the play method. So far, this still refers to the video. It does not refer to the for each or the global call. It does not refer to the window yet. This still refers to the video because it's inside the play method, and the play method is being called by the video. Since it is still inside the play method, it still refers to the video, and the outer this now points to the video, and it's basically telling that anything inside this for each function or anything inside any methods inside this callback have to point to the video. So this, instead of pointing the this keyword on line 15, instead of pointing to the window, now it will point to the video object. Now actually writing dot bind this in every callback is noisy and annoying. Since ES6, we have a much cleaner solution to this. Arrow functions. Arrow functions are very unique. They don't have their own this context. Instead, they inherit this from their containing lexical scope. Let's rewrite our callback. So let me remove this. Again, our function show tags, our method show tags, and inside our show tags, this dot tags dot for each, I'll simply just create an arrow function. And inside our arrow function, I'll log exactly the same thing, this dot title and tag, and I'm taking in tag. If we run it, we get JavaScript coding and JavaScript web instead of undefined. By simply changing the function that we had earlier into an arrow function, the problem is vanished. The arrow function looks around, sees that it is inside the showTags method, and binds this to the video object automatically. This is also why you should almost always try to use arrow functions for callbacks, and you'll see this very prominently in ES6 version of JavaScript coding. So to recap, when calling a method, this is the object. When calling a standalone function, this is the global context or the window. You can use call, apply, or bind to explicitly set this. And finally, arrow functions don't rebind this, they inherit it from their surrounding lexical slope, from their surrounding lexical scope. Mastering just this concept actually eliminates around 80% of weird bugs that you encounter in JavaScript. Understanding this can be really complicated for beginner JavaScript users, but go through this video a few times and make sure that you're asking questions in the comment sections, and we'll get to you as soon as possible. In the next episode, we're actually going to look at modern ES6 classes and see how they make object-oriented programming even cleaner. See you there. Hello and welcome back to episode 9 of Advanced JavaScript series. In the previous episodes, we looked at constructor functions and the prototype chain. We learned how to save memory and we learned how to manually attach methods to a constructor's prototype. This works perfectly fine, but let's be honest. The syntax is a bit chunky. In 2015, ES6 introduced a new keyword to JavaScript, the class keyword. It gives us a much cleaner way to build objects and implement inheritance. But a side note, JavaScript did not actually become a traditional object-oriented language like Java. Classes in JavaScript are just syntactic sugar over the existing prototypal system. So understand that all classes systems are actually based on prototypes in JavaScript. Let's come back here and rewrite the circle constructor that we did using an ES6 class. We'll use a class keyword followed by a name. So this name has to be in Pascal notation. We'll simply directly give curly braces. Inside the class, we have a special method called the constructor. This is used to initialize our objects. It's exactly the same as our old construction function. So you type constructor, and in the constructor, you give an argument that you need for this class to, for an object you made using this class to exist. So radius, and this dot radius equals to radius. Now we learned about what this was in the previous episode. This basically refers to the object or method or window that is calling the function or the object or method. So whatever calls this circle will get a property called radius attached to it. Now what about our methods? Instead of writing something like circle.prototype.draw outside, we actually move all of this inside the class itself. And we can directly do this by simply just making a method inside the class. Simple as that. So we just console log draw. Now, to create a new circle, we use the new operator just like we did before. So C1 equals to new circle 1. Look at how much cleaner this is. All the logic related to a circle, its properties, and its methods are neatly packaged inside a single block. This is your class. C1 is a brand new object that will be created. Earlier, we used something like return to return an object that simply assigned that using constructor functions. But using a class, it works exactly the same. So you call circle with the argument of 1. What is this 1? It actually directly correlates to the constructor function of that class. The constructor function with the argument 1 is called this dot radius, as in C1 dot radius, because C1 is the one that's calling circle right now. C1 dot radius gets a property radius, and it gets a method draw. So at the very beginning, a new object is created. The new keyword creates an object. And inside the object, this dot radius equals to radius. It gets a property radius and the value that has been passed over here. So it gets the value of 1. Now this is specific to every single new instance created. So if I created a C2 or a C3, every single one would have a different radius or could have a different radius. However, the methods, as you can see, are constant for each and every circle. So the methods aren't defined inside the constructor. Anything that's varying or a variable is defined inside the constructor, and all the methods are defined directly inside the body. So every single one just gets the body exactly the same as every single other one. So no matter how many circles I create, they'll all have the exact same body. So this object is created. Now we go ahead and store the object into C1. So a new object const C1 is created with these values. So this is essentially what is being created when we call this line. Now, actually, I want to show you that this is just syntactic sugar. Let's see what a class is actually under the hood. If I console log the type of circle, so what do you think we will get? It's simply a function. To be more specific, it's a constructor function. And what about the draw method? Does it get duplicated on every instance? No, it doesn't. It gets added to the proto or the underscore proto property, and the JavaScript engine automatically takes all the methods defined in the class body and puts it in the prototype for us. So all these methods are automatically put into the prototype for us. It did all the heavy lifting. Where ES6 classes really come in handy is inheritance. So when we did inheritance earlier, it was really messy. We made shapes, we made circles, squares, triangles, but it was really messy. Doing inheritance the old way with prototypes requires writing complex, confusing, boilerplate code. Now it's incredibly easy. So let's create a class called shape. Let's do the same. So I'll create a class called shape, and inside shape we will have a color property and a move method. So to declare properties, you need a constructor function. So the color goes inside the constructor. This dot color equals to color. But methods go directly inside the class body. The method might be move and just print object moves. Let's not say object, let's just say shape moves. Now to make another shape like circle inherit from the class shape, we use the extends keyword. So we can make a class called circle. And we can make it simply extend from the class shape. Now inside it, we have a constructor, and this constructor is actually for the circle itself. What does the circle need? The circle simply just requires a color, and it requires a radius, obviously. Inside it, this dot radius equals to radius, and this dot color equals to color. Now this code has already been written inside the shape class, so why repeat it? So to simply call the constructor of the shape class, or to avoid repeating code that exists inside the constructor of the shape class, or the constructor that is extended from, or the constructor that we're extending from, simply remove this line and call the constructor of shape class by passing in color. If you call the constructor, it simply sets a color property to the color that you passed in, right? So to simply call this constructor, we have a method called super. So inside super, you pass in all the arguments that you need in the constructor of the parent class. So I just need a color. So what super does is it automatically calls the constructor class of your parent and does everything that the parent class is supposed to do, including adding the move method. So any object made with this class currently already gets a move method. So const c1 equals to new circle, and I have to pass in a red color, and I have to pass in a radius, let's say 10. Right now, if I try to access c1.move, this is possible. Shape moves. This is possible even though inside our class circle, we don't have a move method. This is possible because we're extending from shape. And once we call the super, or once we call the constructor of shape, that method automatically gets added to the object. Let's say we didn't call the super and run it now. You actually get a syntax error because this is something that you must absolutely do. Obviously, your circle can have its own method like draw. So draws circle, and I can still access c1.draw, which would still give me shape moves and draw circle. Any object made with the circle class has the draw method, move method, radius property, and the color property. This is how everything combines together. Finally, let's talk about abstraction, which means hiding the details. In a real application, we don't want the outside world to be messing with internal state of our objects. For example, the radius shouldn't be a negative number. For a long time, JavaScript developers used a naming convention. They would prefix a property with an underscore. So the radius would simply just have an underscore to tell other developers, hey, this is supposed to be private, don't touch it. But it actually didn't prevent anyone from changing it. It was just widely understood by developers that any variable with a prefix underscore should not be touched. But recently, JavaScript introduced true private fields. We define them using the hash symbol. First, we declare the private field at the top of the class. So at the very top of the class, we have to declare our private fields. So private fields. What's a private field? Radius is a private field. We don't want anyone else being able to see what private field is. And when we initialize it in the constructor, we use a hashtag. So this dot hashtag radius is the radius. Now keep in mind, you don't actually have to pass in hashtags here, and it will give you an error if you try to do so, because of how objects are created. Again, creates a new key and sets the name of the key to be hashtag radius. It then sets the value of that key to be radius. So this is the value, this is the name of the key. Keep that in mind. This is the name of the key, this is the value. Now, if you try to access this field from the outside, so if I try to console log c1.radius, or actually shoot c1.hashtag_radius because c1 doesn't actually have a dot radius property, we will get an error. Private fields hashtag radius must be declared in enclosing class. It's impossible to read or modify this property from outside the object. Now, this is true encapsulation. Earlier, if you didn't have this hashtag property, right now, what do you think would happen? First of all, it would give an error because a key named radius doesn't exist at all. It's undefined because radius doesn't exist because we have a property called hashtag radius, but not a key called radius. If we remove this and run it, it will simply give me 10. So anybody from the outside world could access this object and get all the values inside the object. But simply by adding hashtag, simply by declaring that this is a private field, if you run it, it will tell you that private fields must be declared and you cannot access it. To wrap up, ES6 classes provide a much cleaner syntax for object-oriented programming. They hide the ugly details of prototype chain, making it easier to implement inheritance with extends and super. And with the new hashtag syntax, we can finally enforce true data privacy. Now we're finally finished with objects. In our next module, we'll look at event loop and how JavaScript manages to run thousands of tasks at the exact same time without crashing. See you in the next episode. Welcome back to episode 10 of Advanced JavaScript. Today we're going to be talking about event loop and concurrency models. Here's a fundamental truth about JavaScript. It is a single-threaded language. That means it has only one call stack and only one thing to do at a time. So here's the paradox. If JavaScript can only do one thing at a time, what happens when we request data from a database that takes 5 seconds to load? Does the entire website freeze? Does the user scrolling stop working? Or does the browser forget to run smoothly? But no, the browser works perfectly fine and runs perfectly smoothly. How is that possible? Today we're going to learn about the event loop in JavaScript. Let's start with a classic developer interview question. Look at this code. We have console log 1, then we have a set timeout with a delay of 0 milliseconds, then we have a promise that resolves immediately, and finally we have another simple console log. Pause the video. In what order will these numbers print to the console? You might think it's 1, 2, 3, 4 because the timeout is 0. Let's actually run it. 1, 4, 3, 2. Why did the promise run before the timeout? And why did 4 run before 2 even though timeout was set to 0 milliseconds? To understand this, we need to zoom out and look at the whole JavaScript runtime. Let's trace our code step by step. Line 1. This is synchronous. It directly goes onto the call stack, prints 1, and then pops off. Line 3. Set timeout. Set timeout is not actually a JavaScript feature. It's a web API. The call stack passes the timer here to the browser's web API to handle in the background, and immediately pops set timeout off the stack. The execution moves on instantly. So as soon as we hit this piece of code, it gets added to the call stack, gets removed from the call stack immediately, and moves on to promise. When we hit the promise, this is also asynchronous. The engine registers the dot then callback to be handled later, and it pops off the stack. Finally, console log 4. This is synchronous. It goes on the stack, prints, and then pops off. This is why 1 and 4 print first. Synchronous code always finishes before asynchronous code. Now, our call stack is empty, but we still have two callbacks waiting. We have the set timeout and we have the promise resolve. Who goes first? In modern JavaScript, there isn't just one waiting room. There are two, the task queue and the microtask queue. Callbacks from the web APIs like set timeout or set intervals or DOM events go to the task queue. So all of these go to the task queue. And all of these go to the microtask queue. These are all the things that go into the web API. So these are not derived from JavaScript itself, but the web API. And these are methods and functions that actually exist inside JavaScript. The rule is that microtask queues have a higher priority than task queues. So microtask queues will always finish first. So to summarize again, let's try to look at this inside the call stack itself. So I'll host the server. So let's look at this in the browser itself. I've added a breakpoint to line number 1. I'll start it by looking at the call stack. If you look at the call stack right now, there's just a global context. There is no other thing added on top of the call stack, although running into set timeout and promise resolve should be added to the call stack in theory, but it doesn't. So if I step in, I'll move on to the set timeout function. Even though I've reached the set timeout function, nothing gets added to the call stack. Why is that? Since set timeout is an asynchronous function that is provided by the browser API, as I've said before, it doesn't get added to the call stack. It gets added to the task queue. So as soon as the browser sees this, it takes the set timeout and puts it on the task queue. Then we move on. Nothing inside is actually executed because that's the task for the task queue. The call stack does not execute this. Then we encounter promise. Promise is also another asynchronous piece of code, so it automatically gets added to the microtask queue instead of getting added to the call stack. So call stack simply ignores this too. So it doesn't go inside it and print console log. That's simply not its task. Then it sees the next line, which is console.log4. Since this is synchronous code, it is executed on the spot. What is executed next? This is executed next. So the microtask queue always has a higher priority than the task queue. So the code inside the microtask queue is executed first. So we get 3. And then the code, and then we go through the task queue. And finally, we reach the set timeout asynchronous function, which is provided by the web API. So in our console, we get 1, 4, 3, and 2. So to summarize, synchronous code runs immediately on the call stack. Web APIs handle async operations, specific async operations in the background, like set timeout and set intervals. We have our microtask queues, which have a higher priority than web APIs, so they execute first before going into web APIs. Then we have our task queues, which is the waiting room for our web APIs. So everything that's included in the web API gets automatically added to the task queue. Then we have event loop. Event loop basically has a simple job that monitors call stacks and queues. It asks if the call stack is empty. If yes, it checks the queues. It looks at the micro queue task first, then it looks at the microtask queue first, then it looks at the task queue, and after both call stack and queues are empty, it finishes the program and says that that's it. That was all for this episode. One last thing that I'd like to infer upon you before you leave is the importance of all of this. So, why do we actually need call stack and queues? It's because if the call stack is blocked, the event loop cannot push user clicks, scrolls, or data that is fetched onto the stack. Your entire application would freeze. That's why we must delegate heavy tasks like these to web workers or break them up asynchronously. That's why we need queues. In the next episode, we're going to take this foundation and apply it to modern syntax. We'll look at how async await completely changes so that we can write asynchronous code, making it look and feel synchronous. See you there. Hello and welcome back to episode 11 of Advanced JavaScript. In the last episode, we learned that JavaScript is the single-threaded and we use web APIs to run time-consuming tasks in the background. But how do we actually get the results of those tasks when they finish? Historically, we have used callbacks. A callback is a function that you pass into another function to be called when the background task is done. In the last episode, we learned that JavaScript is single-threaded, and we use web APIs to run time-consuming tasks in the background. But how do we actually get the results of those tasks when they finish? Historically, we used callbacks. A callback is a function that you pass into another function to be called when the background task is done. Imagine we want to fetch a user from a database, then get their GitHub repositories, and then get the commits from the first repository. We'd have a function, getUser, and inside it, we take the user, we call another function, getRepositories, user.github, username, repos, get commits, then get the first repo, which is by index 0, and then from the commits, we'd console log the commit. So we'd have to do all of this. Look at this. It looks very ugly. It looks like a sideways pyramid. This is famously known as callback hell or pyramid of doom. It is incredibly hard to read, hard to maintain, and almost impossible to properly handle errors in. So what we're doing is we're getting a user first, and it's stored in our user. Then we're getting the repositories of that username, all the repositories, and we're getting all the commits in that repository. We're getting the first repository and looking at the commits and printing it out. So this, by the time we reach this console log, we might have hit 1, 2, 3, 4, 5, 6 different errors. Now you'd have to handle those 5 or 6 different errors inside this block of code, which would make it extremely, extremely hard to maintain. To solve this, ES6 introduced promises. A promise is exactly what it sounds like. It's an object that holds the eventual result of an asynchronous operation. When you create a promise, it is in a pending state. It will either resolve with a value or reject with an error. Let's assume our getUser, getRepositories, and getCommit functions now return promises instead of taking callbacks. So getUser1 dot then user get repositories from the username, right? Then after we get the repositories from the repositories, we would get the commit of the first repo, and after getting the commits of the first repo, we'd simply just console log the commit. You can see how this is already much easier to handle. Instead of nesting functions inside functions, we are chaining .then methods. This execute first, then we execute this, then we execute this, and then we execute this. This completely flattens our code and reads top to bottom instead of left to right. And remember our last episode where we talked about call stacks and queues. All of these automatically get added to queues, obviously because they're asynchronous operations, but they get added to the VIP microtask queues. So we had two different kinds of queues, a task queue and a microtask queue. Microtask queues run before task queues, and task queues are mostly used for web API functions. So since this is not a web API function, it's a promise, it gets added to the microtask queue, which is in the highest priority of queues. And for error handling, you may ask, we simply just attach one single catch, and we catch an error, and simply just print console log error. So if any of these .thens return an error, simply the .catch is triggered and that error is logged out. If any of these promises fail, the execution jumps straight to the catch block. That's a massive improvement over callbacks. Promises are good, but chaining .then everywhere can still feel a bit unnatural. What if we could write asynchronous code that looks exactly like synchronous code? In 2017, JavaScript introduced async and await. This is not a new feature. It's purely syntactic sugar built on top of promises, like how we saw classes that were built on prototypes. To use this, we must wrap our code in a function, and we mark that function asynchronous with the async keyword. So let's get rid of all of this. Actually, let's keep this for reference. And we'll come down here, create a function called display commits. And inside display commit, we want a user, and we call the get user function to get our user. We want our repositories. We call the get repositories user dot username to get our repos. We want our commit, so get commits from the first repos, and we simply want to log the commits. This would work perfectly if this was synchronous code, but since it's supposed to be asynchronous in a database, it's not guaranteed that 100% of the time the database is up or it's going to respond as soon as you call the database. So this get user function may require some time to complete, but JavaScript doesn't wait around. It completes all of this code in microseconds. So it's simply going to dash through all of this code without waiting for any response from a database. So you simply send a signal for the database, but you don't wait for a reply. You simply move on. And doing that, you can see why it would not work. It would return undefined, 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 and your commits would simply just be undefined because you didn't actually get any data back. You already printed the commit before data even got back to your server. That is why we need asynchronous code. Now, how do we make it so that when calling the getUser function, we actually wait for the data to come back before moving on to getting the repos? And we wait for the repo information before moving on to the commits, and we wait for the commit information before printing it. That is using async and await keywords. So simply, you add await keyword in front of all of this. What does adding the await keyword do? It simply just tells JavaScript that, hey, wait for a bit until this promise resolves and then move on to the next line. This is internally a promise. Over here, we actually need to define the function asynchronous by adding the async keyword. Now this will work perfectly. There are no callbacks, there are no .then methods, and it reads exactly like a synchronous program. But under the hood, JavaScript engine translates this back into promises. When it hits the await keyword, it releases the call stack and lets the browser do other things until the promise resolves. So as soon as it sees this await keyword, this gets added to, you know it, a queue. Now there's one thing actually missing here. With our promise chain, we had a .catch block. How do we catch errors using async and await? Because our new code looks synchronous, we can actually use standard error handling methods of JavaScript. That is try and catch. So simply just put all of this inside a block, which is the try block. At the end, get a catch block. Oops, this looks a little bit ugly. And let me just all of this one step. All right. And if we catch any errors, simply just console log error. Of course, you'd have to catch it here. And there we go. Since all of this code runs exactly how it would synchronously, well, it appears to run synchronously, even though it's asynchronous. It runs line by line. So if any error has occurred, the try catch block immediately catches that error and prints it out. We put our happy path inside the try block. So what we desire inside the try block. If any of the await statements fails or rejects their promise, the execution will immediately jump to the catch block. So the old way was using callbacks, which led to callback hell, where you had multiple pyramid-looking structures with multiple error handling and things just dependent on each other in wrong ways, hard to manage, hard to develop, and hard to look at. We moved on to promises. Promises are objects representing future values. It flattened code with dot thens and caught errors with dot catches. But still, it looked a bit disinteresting. That's why in 2017, async and await keywords were introduced. They're just syntactic sugar over promises, which means they just look different, but internally they're all promises, and they make asynchronous code look and feel like they're synchronous by running them line by line. Then we have our try catch, which we can use to catch errors in asynchronous code, just like we did in synchronous code due to async and await keywords. To recap, never write deeply nested callbacks. It leads to spaghetti code. Use promises to flatten your asynchronous operations. And whenever possible, use async and await keywords to make your code clean, readable, and easy to maintain. Now that we know how to write clean, modern asynchronous JavaScript, it's time to talk about organizing our files. In the next episode, we'll look at ES6 modules and tooling, and see how to break massive applications into small, maintainable files. Hello, and welcome back to episode 12 of Advanced JavaScript. Up to this point, we have been writing all of our code inside a single file. For small scripts, that's fine, but what happens when you build a massive application with thousands of lines of code? You end up with a giant, unmaintainable monolith. In the old days, developers tried fixing this by splitting their codes into multiple files and loading them with multiple script tags in their HTML. But this created a huge problem: global scope pollution. If file A defines a variable called config, and file B also defines a variable called config, file B will overwrite file A. Everything is dumped into the global window object, plus you have to load the scripts in the exact same order or your app would crash. To solve this, ES6 introduced module. A module is simply a file, but it has a superpower. Everything inside a module is highly encapsulated. The variables and functions inside do not leak into the global scope. Let's see how this works. Let's move to our circle class into its own file. So let's create a script called circle.js. Inside it, I want a class circle, and since we've already done this before, I will speed right through it. So inside our constructor, we want a radius. This dot radius equals to radius, and we have a draw method. And inside our draw method, we're simply just going to log drawing a circle with radius plus this dot radius. Pretty straightforward. We've already done all of this. So right now, this class is private to this file. If you want to use it in script.js, we have to explicitly import it. We do this by adding the export keyword. Simply just write export class circle. Now importing. Now let's jump over to our script.js. We can import that class using import circle from circle.js. Notice the curly braces. Whenever we have this curly braces, it's called a named import. So this is a named import. We are specifically asking for the thing called circle from that file. So the class called circle from that file. Now we can actually make use of that class. So we can make a new circle with a radius of 10, and we can see .draw. If we run this file, we'll get drawing a circle with radius 10. There's also another way to import. If a file only exports one main thing, like our circle.js file, which only exports our class, we can use the default export. So export default class circle. And inside here, all we need to do is drop the curly braces. If it exports only one thing, then using export default is much more useful because you don't need the curly braces. But if you want to be constant or consistent throughout all of your files, please make sure that you use named import. Both approaches are valid, but named imports are generally preferred in modern teams because they force you to use consistent naming. In our console, we can see the error import declarations may appear at the top of a module. Or if you're in Chrome, you might get something like cannot use import statement outside a module. This is because by default, the browser treats your JavaScript file as an old school script and not a module. So all of your files are actually scripts and not modules. To fix this, we have to explicitly tell the browser that it is a module. So to tell it that it's a module, when we linked our script over here, we use the script tag, and inside it, we simply just add an attribute and call it module. When we do this, two things happen. First, the browser enables the import and export system. So everything can be imported, everything can be exported. Second, it automatically enforced strict mode. Remember episode 8? This means that the this keyword will no longer accidentally point to the global window object. It protects us from silly mistakes. So the this keyword right now never points to the global window object. Now if you come back here and refresh this, then you actually get drawing a circle with radius 10. So you get the proper output instead of an error. Now a quick reality check. When modern browsers support ES6 modules natively, we rarely deploy our code like this in the real world. If your app has 100 different modules, the browser would have to make 100 separate network requests to fetch every single file. This is terrible for performance. As you can see right now, if you go into the network tab, it has to fetch our script.js and our circle.js. If we had 100 different objects, 100 different shapes, so it would have to fetch 100 different files. This is terrible. So what we do is we use tooling, specifically bundlers like Vite or Webpack. These tools look at all your import and export statements, map out the dependencies, and crush all your files together into a single, highly optimized bundle.js file. They even remove code you imported but never actually used through a process called tree shaking. So tree shaking, as you know, so like if there's a low-hanging fruit or if there's a ripe fruit, if you shake the tree, the fruits will fall off. So in a similar way, it shakes off all of the things that you haven't used but you've imported. So to get the best of both worlds, use clean modular files when you write the code and a single lightning fast file for your users. So write all of your modules out as is. In the end, use a tooling method like Vite or Webpack to compile all of those into a bundle and ship it to your user in that way. Now there's environments like Node.js that work with Express and React to make all of this much more simpler with much more usage. So those are definitely things that you need to check out after the series. But if you want your web application to be completely vanilla JavaScript, this is the way to go. So to summarize, modules keep your file scoped and clean. It prevents global pollution. It prevents variables from mixing and matching against each other, prevents you from having to import 1,000 different files into your script directly. Export and import shares code safely between files so that if there are any errors while exporting or importing, it will promptly tell you so while debugging. Then you have type module, which actually makes your file run in the browser by telling your browser to enable modules and use strict mode. So again, to recap what strict mode is, it basically makes your this keyword never point to the global window object. Then you have bundlers like Byte and Webpack that squash all of your module files into one file that you can ship for production. We have officially finished Module 3. You know how to build a clean, modern, scalable code. But what happens when things go wrong? In the final section of our roadmap, Module 4, we're going to look at advanced error handling and debugging strategies. So if you've made it this far into the series, I know it was a rough ride, but you can go back, look over all the videos again, request any clarification, or let me know if I should make new videos on any concepts that you might find confusing. But this is essentially all of the technical knowledge that you will need to be a good JavaScript developer combined with our previous series. In the next module, we're basically just going to look at advanced error handling and debugging. So it's all about errors and debugging. You can go ahead, practice everything that you've learned to this point, and then come back and finish module 4. Thank you for watching and keep coding.